x over dx, which is 1. Therefore, you cannot be able to write it. It's not going to write it because 1 can be just ignored when it is a coefficient. 1 can be ignored when it is a coefficient of a given variable. Well, so welcome in this video, and here we are going to do our next example on how to apply implicit differentiation. Just as we said in our previous video, we apply implicit differentiation in functions where we cannot be able to write the function in terms of y. In this example that we have here, you notice that we have a function x squared y minus y squared x cubed equals to 3. You look at that example and you try to write it in terms of y, it's not going to be possible. And therefore, to use the chain rule, product rule, on those other methods of finding the derivatives is going to prove very, very hard for you. And therefore, that is why we need to learn about on how to find the derivative of such a function using implicit differentiation. So in our previous video, we did an example which was very, very easy, and of course we also showed that that example would have been written in terms of y. But in this example here, it cannot be written in terms of y, and therefore this is how we find its derivative using implicit differentiation. Well, the first step, just as we said, is we find the question mark is we are supposed to find the dy over dx of this function. And therefore, for us to do it very easily, we start by finding the derivative on both sides of the equation. So that is going to be d over dx of the right side, that is x squared y minus y squared x cubed is equals to d dx of 3. Right, so this is going to be a bit challenging because we have a product here and a product here. And I need to tell you something, that whenever you have the derivative of a function like y with respect to x, the derivative is going to be dy over dx. But the moment you have dy over dx or dx of any function x, then that the derivative of this function is going to be dx over dx, which is 1. Therefore, you cannot be able to write, or you are not going to write it, because a 1 can be just ignored when it is a coefficient. A 1 can be ignored when it's a coefficient of a given variable. Well, so we are going to use the product here, therefore, to differentiate these functions here, because there are two functions that have been multiplied. So the first one is going to be, now, how do we differentiate a product? We take the first, multiplied by the derivative of the second, plus the second multiplied by the derivative of the first. And therefore, that's going to be the first, that is x squared, multiplied by the derivative of the second. Just as I told you, the derivative of the second is going to be simply dy over dx. And we add that to the second, that is y, multiplied by the derivative of the first, that is going to be 2x. 2x minus, then we have a bracket here. Now, we are going to have the first, y squared, multiplied by the derivative of the second, which is going to be 3x squared, and we add that to the second. The second is going to be x cubed multiplied by the derivative of the first, which is going to be 2y dy over dx, and that equals to the derivative on the right hand side is going to be 0, because the derivative of a constant is always 0. And therefore, the next task is to make sure that we make this the subject of our formula, or we solve for dy over dx. Right, so let's see. How many terms do we have? First of all, let us open this bracket, because this is going to be definitely a negative. So that is going to be equal to x squared dy over dx plus 2xy, starting with a constant, minus y squared, let me start with a constant, 3y squared x squared. Now this is going to be a minus, let me start with a constant, 2x squared y dy over dx. So our next task is to make sure that we have those terms that have dy over dx together, and those that do not have dy over dx, we take them to the other side, and that's going to be equal to, so we're going to have x squared dy over dx. I want to subtract 2x squared y dy over dx, which should be equal to, now taking this to the other side, is going to be a positive 3y squared x squared, then minus 2xy. So you notice we have on the left side we have two terms with dy over dx. Now since we are interested in making it the subject, then I want us to factor it out. Now using this space over here, then we're going to factor it out, dy over dx multiplied by, we are going to remain with x squared minus 2x squared y, which should be equal to 3y squared x squared minus 2xy. And since we want to remain with this, therefore we can divide both sides by x squared minus 2x squared y, that is 2x squared minus 2x squared y, and this cancels out with this, and dy over dx is going to be equal to 3y squared x squared minus 2xy divided by x squared minus 2x squared y. That becomes the derivative of our function here using implicit differentiation. So how did we go about it? Let's check. So the first thing we did is to find d dx on both sides. d dx on this side and d dx on this side. So the d dx on this side, you notice that this is a product. We have to use the product rule, and therefore that's going to be the first multiplied by the derivative of the second. Derivative of the second, as I showed you here, is going to be dy over dx plus the first plus the second multiplied by the derivative of the first minus, again this is a product, the first multiplied by the derivative of the second plus the second multiplied by the derivative of the first equals to 0, because the derivative of a constant is 0. So our interest up to here is to make dy over dx the subject of the formula. So we are going to find those terms that have dy over dx, bring them on the left side. Those that do not have dy over dx, we put them on the other side. That's exactly what we did here. And then we are going to factor out dy over dx. Factoring out dy over dx, we remain with this function right here inside the brackets, and if we divide both sides by this function here, we remain with dy over dx on one side, and this right here becomes the derivative of our function given here, and that's how we apply implicit differentiation.